All right. Good evening, everybody. My name is Andrés Riancho. I'm from Argentina, and I will be talking about esoteric web application vulnerabilities. First, let me let you guys know that I'm really honored to be in Code Blue. Japan is one of my favorite countries. And a little bit about me. I'm an application security expert. I do penetration tests, source code review, and also a little bit of Python development. I created a software, an open source software called W3AF. That's a web application vulnerability scanner that's going to identify vulnerabilities in an automated way in your applications. That's a project that I've been leading for the last 10 years. But this talk is not going to be about the open source framework. This talk is going to be about vulnerabilities. Vulnerabilities that I identified during the last year, and ones that are really interesting for me because they are not easy to identify. They are sometimes hard to exploit, and are interesting because SQL injection is slowly dying. Cross-site scripting is also slowly dying. And we as security experts need to be able to identify these more complex vulnerabilities in order to keep up with developers, keep up with development frameworks, and different techniques. So why is SQL injection dying? The basic answer to that is ORMs. Most development frameworks like Ruby on Rails, Django have an ORM, and developers are using it. By using an ORM, the thing is that developers don't write SQL queries. If they don't write SQL queries, they are not going to be able to inject or to add SQL injections to their code. Also, in cross-site scriptings, we have templating engines. Templating engines that are going to be used to render the HTML content that you see on your browser. Those template engines, if properly configured, are going to escape HTML by default. So if a developer is sending a user object into the template and rendering that user, the template engine is going to HTML encode the variables, and the cross-site scripting will be prevented. Those things are really something that I don't care about. Cross-site scripting and SQL injections are vulnerabilities that can be found easily by automated tools, are things that should be found by those tools, and you should spend your time trying to find vulnerabilities like the ones that I'm going to explain now. So let's start with the first one. I'm going to go through 5 different vulnerabilities. Those vulnerabilities are completely independent. They are not related. So let's start with the first one. Aggressive input decoding, which is going to lead to no SQL injections. Ruby on Rails and some other programming frameworks are going to decode the HTTP body in an interesting way. So, for example, if we have code like this, that's a handler, an HTTP request handler. What will happen is that this params variable is going to be filled with Andrés or Andrés. Depending on the content type, what will happen is that the input will be decoded. And also, if you send a multi-part encoded body, it will be decoded. If you send in the query string, like here, if you send name equals Andrés, all of that will end up in the params variable. That's good for developers. That's actually really good. It helps abstract all of the sources of information and centralizes everything in params. For security, it's not that good. And let's understand why. In here, you'll see that in the JSON body of this request, I changed it a little bit. And instead of sending a string that I was sending here, I'm now sending an array. And what happens is that because of Ruby on Rails aggressive input decoding, it will translate that JSON information into a Ruby hash. All right? So that hash in Ruby will be a completely different structure in memory than a string. Now, let's try to understand something different from the previous one. The aggressive input decoding plus this will end up in a NoSQL injection. In Ruby on Rails applications, you can have SQL databases or NoSQL databases. If you use NoSQL, most likely you are using MongoDB, and by using MongoDB, most likely you're using Mongoid. Mongoid is just an abstraction around the Mongo database. And developers can write something like this. You have the object, you apply a filter, and pass a couple of user-controlled parameters. If this HTTP request is sent and handled by this code, what will happen is that registration.where is going to perform a filter with this token and this user ID. Until now, everything works as expected by the developer. But if we also know that complex filters can be written in Mongo in this form, you would see that it's saying $, not equals Argentina. That means that Mongo is going to filter all of the users that don't have Argentina as their country name. And something similar happens here with user ID in this list. Okay? So now, if we add the two different things that I explained, if we add the aggressive input decoding plus the kind of complex Mongo filters, we get to this. It's possible to perform an HTTP request that's going to be like this. Token equals not equal, no match. If we send that here, what's going to happen is it is possible to, without having a valid token and only by having the user ID, it's possible to force this piece of code in order to retrieve objects from the database by performing a NoSQL injection and completing the registration process without having the token. Okay, make sense? Yeah? All right, how to solve this? Basically, to solve this, there are different ways. The easiest one, but it's not very complete, is to add this, the toString. The idea there is to cast all of the parameters that we are receiving from the attacker. We cast them to strings. So if the attacker is sending a request like the one that we saw before, with an array, we cast it to a string, and it's actually going to be a string that contains special characters. But the issue there is that developers need to remember to add the .toString to every parameter that they receive before using them in NoSQL queries. And that doesn't scale because developers are going to forget about that. So there are two different Ruby on Rails gems that you guys can use. One is Sinatra Param, which is going to strictly validate the type of each input. And another one is to use strong parameters. There's a gem that applies strong parameters to Mongo queries. Strong parameters is already supported for SQL databases by Ruby on Rails, but it's not for NoSQL database. All right, that's how you fix it. Let's talk about a different vulnerability, host header injection. This vulnerability is kind of known, but in this scenario, I was able to find an interesting way of exploiting it. So this application that I was testing performed two-factor authentication by calling my cell phone and sending me over the call a code. That code, I had to enter the code into the application in order to verify that I was holding the cell phone. All right? So it's two-factor authentication, nothing really strange. But I wanted to bypass this system. I wanted to bypass the two-factor authentication. In order to do that, I needed to understand how it worked. So I started to read the source code, and I created this very beautiful graphs. First, we have the application, the vulnerable web application, that's going to perform a request to a software as a service. This software as a service that we see here with a small telephone is, for example, Twilio. Twilio is used to perform calls or send SMS messages. Basically, it's a software as a service that can be used to perform audio calls to real phones. So in this case, the vulnerable web application was sending a request to the API saying, please call this phone number, and the audio for that call is going to be available at this callback URL. So the software as a service went to the vulnerable web application, retrieved the audio call, then initiated the call to the user, and of course, in this audio, there is the code that we want to steal. And then in the audio, the code was sent to the user. Finally, as I said, the user enters the code in the application, and the identity is verified. In order to attack this, there are different vectors. One could try to hack the user's cell phone in order to capture the voice. One could try to hack the cell phone tower in the area where the user is, or try to hack Twilio. Actually, all of those options are kind of complicated. So I tried hacking the vulnerable web application. And it's vulnerable.com, so it should be vulnerable, right? One of the things that I tried was brute forcing the audio files. But it doesn't look that it's going to work. They are using unique IDs generated randomly. So it's very, very difficult for me to be able to, via a brute force, identify a file, an audio file. And even if I could access that audio file, it would be impossible for me to know for which user that audio file was. So what I did was to keep digging, keep trying to understand how the system worked. When a new phone call was initiated, this is the post request sent from the vulnerable web application to the software as a service. In here, we see the phone number and the audio callback. Trying to understand how that was generated, I got the source code and saw this. Start call is going to perform the request, the post request, using the requests API. for the request module for Python, sorry. And there is a vulnerability here. The issue is that request.host is controlled by the attacker. And that request.host controlled by the attacker is used to create the callback URL. Because of that, it's possible to do something like this. Instead of sending the original HTTP request, what I did was to modify the request and set host evil.com. I'm creating the HTTP connection to the same IP address, to the same port, but I'm using a completely different host. What happens next is that the vulnerable web application is going to create a call to the software as a service, and the callback URL is now completely different. It's not vulnerable.com, it's evil.com. That means that Twilio or any other software as a service that's on the other side will try to get the audio for the call from evil.com. That's the second step that you're seeing there. Once we receive in evil.com the request with the ID, we forward that request back to the original destination, which is vulnerable.com. We retrieve, as an attacker, we retrieve the audio in here from the vulnerable server, and in the audio we get the verification code. So with this vulnerability, we were able to bypass the second factor authentication implemented in that application. The solution is fairly simple. In Django, for example, there is an allowed hosts setting. That allowed hosts is a whitelist of all the domains that your application should respond to. If Django receives an HTTP request that has a host header that's not in that list, it's going to throw an exception, and nothing else would happen. In this case, where I found the vulnerability, allowed hosts was set in production to a wildcard, which is completely insecure. If you're doing application development in different languages, different frameworks, allowed hosts might not exist. So you will have to configure your Nginx or your Apache servers in the same way. They should have a whitelist with all the domains that it should accept. All right. Third one. In this case, we're going to be abusing the aggressive input decoding in order to bypass a password reset token validation. So password resets are really interesting. Password resets are really simple if you explain them to somebody, but then even semi-senior developers tend to introduce vulnerabilities to the flow, to the password reset flow. And those vulnerabilities, in some cases, can be abused and exploited into hijacking another user's account. And this is a good example of a very simple vulnerability that if you are not reading the source code, it's difficult to identify. And if you're not very interested and concentrated with that source code, it's also difficult to identify. So password resets. The basic idea is you're a user, you don't know your password, you go to your application, your favorite application, and you say, my email address is abc@def.com. Then the application is going to send you an email to that email address. And in the email, you have a password reset link with a unique token. You click in that link, and the application is going to verify the token and give you access to reset your password. Very easy. So let's see how it was implemented in this application and what we can do as attackers in order to gain access to different accounts. So first here, what we are seeing is that each user in this system is going to have in his model, in the database, it's going to have a column or an attribute in the model that's going to be called password reset token. The type for that column is a string, and the default is nil. This is the code that is going to be used in the password reset process. First, we see start password reset. That's the URL that receives the user's email and verifies that the user exists in the system, and then sends an email to the user. All right? So we verify that the user exists. We generate a token. We assign the token to the user. Save. Send the email. So the user receives the email in his email address and clicks on the password reset link. When he clicks there, the code that's run is here, complete password reset. What happens there is that the password reset token sent by the user is used to perform a filter here. And then if the user exists, if the token for that user exists, we're going to set the new password, set the password reset token to nil, and save. So the vulnerability here is that we, as attackers, can force the application into doing something completely different and unexpected. In this case, we're going to abuse the input decoding, the aggressive input decoding performed by different frameworks, in order to send an HTTP request like this one, where we set token to null. By setting token to null, we are, and by knowing that the default value for the password reset token in the database is null, we are exploiting this line into selecting the first user in the database that doesn't have an initiated password reset flow. So like we saw here, once you finish your password reset flow, your password reset token is set to nil. And if you never even started one, it's also set to nil. By sending token null and having this code, what we are doing is choosing from the database the first user that has password reset token equals to null. That's going to be any user in the system. As an attacker, I don't care which user. I'm going to logging in. I'm going to reset the password for any user and then sign in as that user. OK? So the issue there is that because of the aggressive input decoding that we see here and here, and because the developer is not taking this into account, it's possible to hijack any account in the application. In order to fix this vulnerability, the developers need to change two different things. And most likely by changing only one of these two, it's going to be OK, but we need to make sure. First, we apply the toString here, and then we are going to set the default to generate random token. That's much better than setting the default to nil. OK, makes sense? Are you guys following me? Yep. Cool. All right. So number 4, In this case, I'm going to explain how a merchant can implement its integration with PayPal in an insecure way. The basic idea here is that when a merchant is selling something and wants to integrate and have their users pay with PayPal, he needs to perform a couple of steps. One of the most important steps is to develop an IPN handler. Each time that PayPal processes a payment, PayPal is going to send an event to the merchant using an IPN URL. So in this example, example.com/PayPal handler is the IPN URL. It's the place where PayPal is going to send all of the new information about that merchant. New information like, for example, the payment for this product failed, or the payment for this product succeeds. Okay? IPN is fairly simple to implement, but there are a couple of security features which need to be taken into account. So this is how it works. Basically, the merchant has a button in his site that says pay with PayPal. So the user is going to, for example, add different things to his cart, and at some point, he's going to click on the pay with PayPal button. When that happens, the user is redirected to PayPal. That's here. The user is redirected to PayPal. The user pays, enters his credit card information, enters his bank account information any way that's allowed by PayPal. And finally, what happens is that if the payment succeeds, the PayPal server is going to send a post request to the IPN URL in the merchant server. The merchant is then going to say, all right, I need to verify if this HTTP request was sent by PayPal or was sent by somebody else. I need to verify all of this information that I just received. So the merchant does the verification step in here. That verification step is basically taking all of the parameters from the IPN handler and sending them back to PayPal and asking, is this valid? Is this transaction valid? And PayPal, if it's valid, it's going to return verified. And if it's verified, the payment is processed. All right? PayPal's IPN request is fairly complex. It has a lot of parameters. This is how it looks. The basic idea here is that PayPal is sending this request to the merchant, and there are a couple of interesting parameters that we're going to analyze. First, we have MC gross. That's the amount that the user paid in PayPal. Payment status is basically something that says if the payment was successful or not. And then we have two interesting things. Receiver email. That's the email address for the PayPal user that received the payment. And finally, custom. Custom is an ID. It's something that is set by the merchant. And when creating the Pay with PayPal button, the merchant can set any value to the custom parameter. So it's a parameter that the merchant creates and adds to the button. So when the user clicks on Pay with PayPal, it's going to be sent to PayPal. After processing the transaction, PayPal is going to send it back through the IPN to the merchant. And that's the way in which the merchant is going to be able to associate a payment with a user, all right? That's a way of kind of syncing everything together between the merchant and the user. That's custom, all right? In this case, it was the user ID. It could have been the user's email. It could have been the card ID, anything, all right? And as I said, what we want to do as security conscious developers is verify that information. We are receiving information from PayPal. We verify it by performing a request to the PayPal API, and we get the result saying verified. And only then we perform the transaction. And this is how it's implemented. In this case, it's insecure. It's performing the validation. It's performing the verification because it's doing the HTTP request to this URL. But there is a bug here, and I'm going to explain it now. The request post sends the parameters. If the response is verified, then all of this. The issue here is that the merchant is not verifying that the event is for his account. So an attacker can perform these steps. An attacker can perform these steps. He can create a new PayPal account. He can create a IPN, he can configure an IPN URL pointing to evil.com. Then he creates a pay with PayPal button using the custom ID that he got from the merchant. And he pays using the attacker's credit card. He pays to himself in order to receive an IPN event from PayPal. That IPN event and all of the information he receives in evil.com are going to be valid and are going to be valid for doing this. The adversary can send all of the information he got in evil.com IPN handler. He can send it to the merchant. The merchant will verify it, will check if it's valid, and it will actually verify as true. That happens because this line is not there. This if parameters receiver email equals merchant PayPal user. Just remember that something that we did in this attack is to get all of the information from a payment that was for an attacker that's valid for PayPal, and we send it to the merchant. So the merchant is failing to do this check, and that's why we get the vulnerability. In this case, what happens is that the attacker will perform a payment. He will actually spend money using his credit card. But after spending that money, the money is not going to go to the PayPal account from the merchant. The money goes to the attacker's PayPal account. And the merchant is going to believe that he received a payment when he actually did not. That's why it's possible in some implementations to perform a double spend of that money. The attacker, the good thing for the attacker is that he is paying, he is getting the services or the goods from the merchant, and he's not paying for them. And actually, I went to GitHub and I tried to identify different vulnerable IPN implementations, and they are many. At least I found 5 in 2 hours. So if you guys have the time, you should go to github.com, search for PayPal IPN, and identify this type of vulnerability. Once you identify it in one of the many, I don't know, like WordPress PayPal modules or WordPress PayPal plugins, or for Drupal or for any other e-commerce site, what you should do is, of course, report them to the developer, and then maybe try to identify applications on the internet which are using that software, and also report the vulnerability to them. Never exploit this and buy for free, okay? So one of the most common questions that I get after finishing this talk is this PayPal's fault? My answer is that partially, yes. Because the IPN implementation, the design of the IPN protocol, in my opinion, is insecure. Because it's delegating many security checks to the merchant. It's actually making the merchant verify the message, verify that the receiver email is correct, and the merchant may or may not perform those steps. And by changing the design of the IPN protocol, it's possible to avoid those vulnerabilities. One of the clients that I have is Mercado Pago. Mercado Pago is a payment gateway in Latin America. And those guys implemented IPN the right way. What they did is, instead of sending all of the information from the payment to the IPN URL, what they did was to send just the ID for that event. Then what the developer needs to do is, with the event ID and the API key for Mercado Pago, go to that API and retrieve all of the event information. If I, as an attacker, send any ID to the IPN handler that's properly designed, what's going to happen is that the IPN handler will go to Mercado Pago, try to get the information for that ID, and if the ID is for a different user, it's not going to work. Okay? So this is partially PayPal's fault. I reported this to PayPal. They said that for historical reasons, they can't change this. The basic thing here is that if they change it, if they deprecate the IPN protocol as it is, many integrations will break. So they are not changing it for now. Okay, number 5. We are getting closer to the end. And we have a lot of time. All right, so in this case, I'm going to talk about a remote code execution in a Ruby on Rails module. Ruby on Rails implements something called active support message verifier. So if you have two different parts of your application or two different applications that need to send messages between them, those messages use the browser, the user's browser as a medium, and you don't want the user browser or an attacker changing that message, you need to digitally sign the message that goes from one part of your application to the other. Digitally signing those messages can be challenging, and also serializing the messages that you want to send could be problematic. So that's why message verifier exists. Message verifier is going to allow you to take a message, any message, any object, serialize it, sign it using a secret, and then send it to the user. Afterwards, the user can send back that signed message to the application, and you can verify the signature. In the process of verifying the signature, you are making sure that there was no modification in the middle. So in this case, what we are seeing is this is how a signed message looks like. The first part is base 64 encoded, and the second part is the signature. And of course, it can be decoded, right? It's not encrypted, it's simply signed. What happens when the application receives a message like this and wants to verify its integrity? It's that the application will first base 64 decode the message, apply HMAC to that message using the secret, and compare the signatures. If those signatures are equal, they match, then the base 64 decoded string is unmarshalled, and the object is returned to the user, to the developer. So the vulnerability here, if you guys have been doing any serialization attacks, is pretty simple to understand. Ruby on Rails documentation, and Ruby's actually documentation, states that unmarshalling arbitrary objects might lead to remote code execution. So if we as attackers can control that base 64 encoded marshaled object, we are going to be able to perform remote code execution on the web application. But we can't simply change that object in any way, because we don't have the secret for signing that object that we want to send to the application. What I found in at least 2 different applications was that developers used really weak secrets for signing active messages. Those really weak secrets, one was hug me, I feel lonely, and the other one was the user ID, which was a number of 5 digits. So as an attacker, then what I can do is, once I identify the secret, I create a specially crafted gadget or object that, when unmarshaled by the application, is going to execute remote commands. Then, and because I have the secret, I'm going to take that specially crafted object, sign it, and send it to the application. Because of everything that I explained, what happens next is that the attacker gains access to the application. It's possible to execute remote operating commands using this vulnerability. In order to fix this issue, 2 different things need to be done. First, if you're going to use this module in Ruby on Rails, choose a randomly generated secret to sign your messages. That applies actually to every secret that you ever generate. But in this case, choose randomly generated secrets which are really long. And finally, something else, instead of using the default serializer for message verifier, you should use the serializer that's JSON. In some cases, it won't work, but in most, it will. So serializer JSON is going to replace the insecure Marshall serializer, and things are going to be safer. Even if an attacker is able to get get brute force or in some other way access the secret, if you use serializer JSON, the remote code execution does not exist. All right. So because of this is that I don't care about cross-site scripting and SQL injections disappearing. Actually, I love that those vulnerabilities are disappearing. I don't really care if SQL injection dies tomorrow, because we are able to find more interesting vulnerabilities. We are able to find things that are really worth it. As I said before, use your tools, but you are smarter than your tools. Use your tools in order to perform the automated part of the vulnerability detection process. Use your tools to do the grunt work, the things that are repetitive. But use your time smarter. Use your time to identify vulnerabilities like the ones that I mentioned. Also, an interesting thing to notice is that most of these vulnerabilities I was able to identify using source code review. Ask your clients to give you the source code. If they don't give you the source code, show your client this presentation. And they will hopefully understand. Finally, you're smarter than most developers. Even if they are trained in security, and even if they are senior developers, they are going to introduce vulnerabilities in the code. They are not going to introduce SQL injections. They are not going to introduce cross-site scripting. But these things, I guarantee they are going to be introducing into the application. All right, that's it. That's my contact information. If you have any questions, I will be outside, and I will be around the conference all day. Thank you.